In this video, we're going to go over the basics of equilibrium. If you move on to organic chemistry, AP chemistry, or just pretty much any chemistry in the future, you are going to definitely encounter equilibrium. Even in AP Bio, they talk about equilibrium. So we're going to go over the basics of equilibrium and what it means and some important principles. So we're going to cover two sets of notes here. So it might be a long video, but this is very important for your understanding of equilibrium. So first thing is that very few chemical reactions proceed to completion, meaning that they use up 100% of one of their reactants. Rather, reactions are reversible. Every single chemical reaction is reversible. I always think of compounds as being made up of Legos, and that you can take them apart and build them up in lots of different ways. And so reactions actually proceed until the rate of the forward reaction is equal to the rate of the reverse reaction. And the example that I always use in class is that scenario when you're on the highway and you look over at the car next to you and it appears that they're not moving, but it's just that you're traveling at the same speed. So it appears that nothing is moving, but in fact you really are. So when a system reaches equilibrium, the reaction actually never stops. The forward and reverse reactions just occur at the same rate, therefore it appears that nothing is changing. Okay, now to figure out equilibrium, there's something called an equilibrium constant, and it's has a symbol of a big K. Okay, and K is equal to the products divided by the reactants. So if I want to write the K expression, we have our products C and D, and we specifically care about them in brackets. Brackets mean molarity. So we want to put C in brackets, the concentration of C, the concentration of D, divided by the reactants A and B, and they're just multiplied by each other. Now, the only thing that's a little bit different here that we probably haven't done before is that C has a coefficient of 3, so its exponent is going to have a coefficient of 3. D has a coefficient of 4, so that means that its exponent will have a coefficient of 4. A has a coefficient of 2, therefore it'll have an exponent of 2. And then B has a coefficient of 5, so its exponent will be 5. So if we look at this other reaction here, we have NH3 to the second power, that's its coefficient. H2 is to the third power, that's its coefficient. And then N2, even though we didn't write a 1, it is to the 1 power because that's its coefficient. Now, what we've set up is simply just a ratio. This ratio tells us the extent of the reaction after equilibrium has been reached. So, meaning, did we form a lot of products? Or did we really not do a whole lot and we still have a lot of reactants left over? So mathematically, if K is greater than 1, that means our numerator, which is our products, is big, which means we formed a lot of product. And then if K is less than 1, we're reactant favored, meaning my denominator, which is my reactants, is big, which means we formed little product. Okay, meaning we didn't form very much. Okay, now the one thing that's a little bit weird here that I'm going to highlight in red is that we omit solids and liquid water. They have constant concentrations, and that's going to come up later. Okay, that's just something some people forget, at least at first while they're learning equilibrium. Okay, so one says write the equilibrium constant expression for the following reactions. So K is equal to the concentration of NO2 to the 4th power. We have no more here. So we need to go to my reactants. I have N2O to the second power, and I have O2 to the third power. In B, we have our K expression, K equals NO2, except here NO2 is going to be to the second power. We have N2O. N2O has a coefficient of 1, so you can write the 1 or you don't have to. And then oxygen is kind of strange here. It has a coefficient of 3/2, so it goes to the power of 3/2. And then in C, we have N2O now on my product side to the second power, O2 to the third power, and then NO2 to the fourth power. Okay, so calculate the value of the equilibrium constant, which is K, for the following system given the data shown. So what I'm first going to do is I'm going to write my K expression. K is equal to H2O times CO divided by H2 divided by CO2. Now, if this water was liquid, this would not be included in my expression. But it's not a liquid, it's a gas here, so we're good to include it. When you plug things in, I think it's helpful to check things off. So I just plugged in water, check it off. 0.5 molar. I'm going to plug in carbon monoxide, that's 3. Now, with brackets, you can write 3M in brackets, but if you just wrote 3 in brackets, those both mean the same thing. Brackets mean molarity, so you don't need to always write molarity if you have brackets. We're going to divide that by H2, which is 1.5. And then we're going to divide that by CO2, which is 2.5. Okay. When I'm going to solve this out, I get 0.4. This tells me that we form very little amount of product. Why? And a good justification is because K is less than 1. Now, one thing I don't know that I used is K, or I don't think I said this, K has no units. So that's very nice. K will never have units. Okay, in 3, it says that we have chlorine molecules. Those are these guys. They will dissociate at high temperatures into chlorine atoms. So at 3,000 degrees Celsius, for example, Kc, which is another way of saying K with using concentrations, for the equilibrium shown is 0.55. So K equals 0.55. If the concentration of chlorine molecules here is 1.5 molar, calculate the concentration of chlorine atoms. Okay, so watch how we're going to do this. We're going to write the K expression. K is equal to the concentration of Cl squared over the concentration of Cl2. We're going to plug in what we know. We get 0.55. That equals X for Cl squared divided by 1.5. I'm going to multiply each side by 1.5. And I get 0.825 equals X squared. I'm going to take the square root, and X is 0.908 molar. Okay, so the concentration of Cl is 0.908. To me, this might be hard to see right now, but this makes a lot of sense to me. We form very little product because K is less than 1. And so X, when I solve for it, it should have been less than my Cl2, which was 1.5. So that makes sense to me. Now, the second half of this video, we're going to go over something called LeChatelier's principle. And what this talks about is how to shift a reaction or how to manipulate a reaction. So at equilibrium, the concentrations of substances always produce K, which is a ratio. If you disrupt a system at equilibrium, such as adding or removing reactants, the ratio for K will be disrupted and the system will be out of equilibrium. But systems will always adjust to achieve equilibrium again. So we are going to shift in the direction that minimizes the disruption that occurred. Okay, I can't spell. So let's see how this works. I've got a reaction here, and as I'm doing this, I do not care about the arrows. I am more concerned about just if you know that it shifts right, left, or no shift. Okay, so if we shift right, that means we're going to form more calcium oxide and more carbon dioxide. If we shift left, that means our reaction is going to form more calcium carbonate, and in the process, we're going to consume the other side. Okay, so watch how this works. If I add carbon dioxide, I've now disrupted my system at equilibrium. I have too much carbon dioxide, so I need to go away from my disruption, which was adding carbon dioxide. So to do that, I can consume carbon dioxide by shifting left. What about if my disruption is to decrease carbon dioxide? Now I don't have enough carbon dioxide to be at equilibrium, so I need to form more. The way the reaction forms more is to shift to the right, because when we shift right, we will form more carbon dioxide. Now, if I add calcium oxide, a lot of people would say you have too much calcium oxide and that will shift left. However, this is no shift because CaO is a solid. If you remember what I highlighted in red on the first page of these notes is that solids and liquids do not affect our equilibrium. If I increase temperature, that means heat has gone up. I have too much heat. I need to consume heat. So to do that, the reaction will shift backwards or shift to the left. Now, here's the trickiest one, the volume one. That one is always tricky. So try to get this down because it's just really hard. If I decrease the volume, my pressure, specifically gas pressure, goes up. So what I want to think about is my gas has gone up, and when carbon dioxide goes up, we will shift left. We'll do more of those on this second example. And then if I add a catalyst, this is going to be no shift. A catalyst only speeds up your reaction. It gets you to equilibrium faster, but it doesn't change where your equilibrium is located. Okay, so let's do a couple examples. If I add PCl3, now I have too much, I need to consume it. I'll shift right. If I remove some Cl2, now I need more Cl2. To get more Cl2, my reaction will shift left to form more Cl2. If I remove PCl5, I need more PCl5, so I'll shift right. Here's where we go. The hard one, decrease the volume of the container. We decrease the volume, the gas pressure increases. So this one goes up, and this one goes up. This side has 2 gas moles. This side has 1 gas mole. And so if I want gas, I forgot to say pressure here. If pressure is what my disruption was, having too much pressure, I want to shift to the side with less pressure. To do that, I'm going to shift right because that side has less pressure. Okay, and then an E, addition of helium without change in volume. Helium has nothing to do with this reaction. Helium is what's called an inert gas, meaning it does not react. That's what your noble gases are. So whenever you see a situation like that, it's going to be no shift. Okay, we're going to do number 2, and then we'll call it quits here. If I add CO2, we're going to shift right. If I add water, water is a gas. If it were a liquid, it would be no shift, but since it's a gas, we're going to shift left. Catalyst is going to be no shift. That just gets us to equilibrium faster. If I increase the temperature, we're going to have to shift right. If I decrease the temperature, we're going to shift left. And then if I decrease the volume of the container, the pressure increases. And so up, 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 and up. This side has 2 gas moles. This side has 2 gas moles. Neither side can actually lower my pressure, so this would be no shift. Okay, I know I lied. I said number 2 would be the last one. I want to do number 3 because that one's a good one. If I add N2O, it'll shift right. If I remove O2, we'll need to make more O2. The way we do that is by going left. If I increase the volume of the container, pressure will drop. Okay, so this goes down, and this goes down. This side has 3 gas moles. This side has 4 gas moles. 3 gas moles versus 4 gas moles. If my pressure is dropping, I want to reverse whatever my disruption was. My disruption was pressure dropping, so I want more pressure, so I want to shift to the right. And then adding a catalyst will be no shift.